Hello and welcome to our expert webinar. Silicon carbide semiconductors in the field of e-mobility are currently a very exciting topic. Cooling or junction temperatures above 200 degrees are just two of the many aspects that need to be considered. It's great that with Tobias Keller we have a proven expert on this topic in our webinar today. Tobias is Vice President and Head of Global Product Management Semiconductors at Hitachi Energy in Lenzburg, Switzerland. My name is Eric Rehmann and I'm responsible for marketing at GVA in Mannheim. This webinar is part of our expert series in which we are happy to share our knowledge and that of our partners on new products, technologies and findings from the field on a regular basis. Also check out our website gva-power.de and register for the webinars that interest you. Or simply visit our YouTube channel and watch the video recordings at a later time. During the live webinar, please feel free to use the chat function of our online portal and ask your questions. We will be happy to address them after the presentation. But now we go live to Tobias Keller in Lenzburg. Tobias, I hope you can see and hear as well.
Hello, good morning, good afternoon, good evening, everybody. I can hear you clear and loud, and I hope you can also see me now. Perfect. Good. Warm welcome from my side. It's a pleasure to have you in this webinar today. As already mentioned by Eric, the topic today is power semiconductor for future e-mobility applications. And I would like to give you an overview what products we as Hitachi Energy can provide here. If there are questions, as already mentioned, please use the chat function and I will be glad later on to come back and answer these questions. Of course, there is also a possibility to send emails later on if there are certain questions popping up later. Let's start with the environment as we see it as Hitachi Energy in e-mobility. 4 or 5 years ago, when Hitachi Energy decided to go into the field of e-mobility, we tried to summarize this environment, how we see it. For you as background information, we have a lot of experience as Hitachi Energy, former ABB Semiconductor, what you actually are, with e-mobility in terms of traction. So we have been delivering power semiconductors for traction application many years, even decades, starting with GTOs, IGCTs, as well as afterwards IGBTs, lean packs, high packs, whatever. And 4 or 5 years ago, within one of the strategy meetings, we sit together and we recognized obviously that there is an e-mobility market segment coming up with early cars, also towards buses, trucks. And we tried to transfer what we already know and the experience we had from the e-mobility traction, also from the railway segment into this e-mobility area. We saw many commonalities, but we also saw some differences. And that's exactly what is shown here as well. So the target was clear, to have a platform of devices to be able to cover a power range between 100 and 500 kilowatts. To have this possibility to have it split for one axle or for two axle. To support, especially at that time, it was not very clear what's happening with the battery voltages, 400, 800 volt, and also very clear silicon and silicon carbide. It was already clear at that time that silicon carbide, 4 or 5 years ago, silicon carbide will play an important role. As you most probably are aware, one of the market early entrants in e-mobility, they already decided at the very beginning to go with silicon carbide. From other areas, we saw still silicon. This has then interestingly completely changed to silicon carbide, where we saw that all the requirements coming from the different platforms were based on silicon carbide. Now I think it's once again leveling more silicon carbide, maybe on the main axle, silicon on the other axle. And with this platform and the strategy we already set up at that time, we were able to address that. A very important topic, and also a topic we spent a lot of time on, we will see that also later, was the cooling. Also it was very obvious compared to the setup what you are using in a locomotive or in a train. The setup in terms of cooling for e-mobility for cars, buses and trucks is completely different. and we'll also come to that later on. What came on top, especially now with the newer chip generation, in the newer silicon carbide chip generations, we also clearly see that also junction temperatures can go higher now. Already at that time, when we started with this platform, we designed the whole platform in such a way that we are able to handle up to 200 degrees C junction temperature. And as many of you might know, that was a rather wise decision, because now we see really these chips either limited for several hundred hours or even unlimited availability for 200 degrees C junction. On top of this e-mobility platform for the rolling application in the car, in the bus, or in the truck, it is very obvious, and we see that even more and more, that in parallel there is also the charging infrastructure part of this e-mobility segment. And at the very beginning, we saw an interesting trend that for the charging, different power modules were used than for the traction train. In the meantime, we see a consolidation that more and more same modules, what are also used in a rolling stock application on the vehicle, that they are also used for charging. I think that makes sense. It's also clearly to be understood that this has also volume effect. Also from this point of view, this e-mobility platform itself is also covering the charging. The product itself, many of you might know, and you might have read it about. It's the so-called roll pack. That's the e-mobility platform. It's a fully overmolded module. It has no gel inside anymore. It can support silicon and silicon carbide, as I already mentioned. It's a half bridge. And one of the results, what we just saw before out of the strategy platform we set up, was also that it has a directly integrated pin-fin structure. So you see underneath here, we see the pin-fin structure. Main connection terminals, either with holes here, that's typically for designing, if you need to easily connect cables for first tests. Later on, for serious production, we recommend not to use the screw type connection anymore, but to go for welding, and then there are no holes in it anymore. We have the different current ratings. What is important to be mentioned, and I think you also know it, you have most probably heard it also a year ago, it is always the same footprint, it's always the same size of the module. What we are varying is the number of chips. We can go up to 2 times 10 chips in parallel. 2 times because it's a half bridge, lower side, upper side, or low side, high side, and then we have each 10 chips in parallel. What is new is the fact that we spread out the silicon carbide chipsets we are supporting. For us, it was always very obvious that security of supply in this area is very important. It's even a must. Also, no matter what happens, you need to be able to get the devices. And therefore, we started very early to integrate different silicon carbide chipsets. And as you can see here, currently we are supporting Wolfspeed chipsets up to generation 4, SD Micro, and we have also our own Swiss Hitachi Energys chipset. As we have 3 different chipsets. Many of them can even match each other. That means you can qualify 2 devices. They look exactly the same outside, but they have different chips inside. And then we can work with active second sourcing. That means one is delivering 80%. One chipset is used in 80% of the roll packs, another one 20%. They are electrically matched and they are both qualified. And if there's disruptions or whatever, then we have the chance that we can seamlessly change over. You see here also 1200 and 750 volt, also still both supported, also for the 400 volt battery, and for the 400 volt battery, we have also the 2 independent chipset suppliers available here. What is slightly newer is the downscaling. If you have a look at the other slide, if you see these currents, they are rather high, 2 times 6 chips, especially also with a generation 4 chip as an example. You're reaching a very high current. For many applications, it's just too much current. You don't need it. For buses, trucks, it still might be suitable, but I mean for a regular electric vehicle, medium range or so, it's most probably too much. And therefore, we also add the RowPack XS. It is same arrangement of connections, has also the pin fin, but it is scaled in both directions. Thickness is the same, but both other dimensions, they are scaled to to have not too much space left in the module and not being covered with chips. And here we're going up to 2x4 chips. Once again, also here, not even explicitly mentioned, but supporting exactly the same chipsets from the same suppliers as in the slide before. Just as a kind of wrap-up summary, what is this module about? You see here these different ranges with the S, M, and L. Please keep in mind the current range, what is given there with the 580, 780, 980 amp. Obviously, that also depends on the application profile, on the mission profiles you're using. It depends on the duty cycle. It depends on the temperatures, cooling inlet as an example. Therefore, it is more a range and not really a single value. But of course, we can support you together with GVA if you have certain requests. If you have an application, we can help you to make sure that you will get exactly the size of the road pack you need. If you go inside the road pack, the strain inductance is at 5 nanohenries, and that's the maximum value. Also, that's a value we can always reach. We are with some optimization. What we are continuously doing, we are even going down now. We keep the 5 nanohenries as maximum, but we are very close to 4. That helps a lot for the fast switching. Also up to 20 kilohertz, absolutely no topic. That's what helps here a lot. The module itself inside has a double chip sinter topology, as that means we sinter the chip to the substrate with silver sintering, and on top of the chip, you can see it on the second picture, you have the possibility to have the die-top system. That's a thin copper plate, and also this die-top system is silver sintered to the chip. Also we have no solder connections in this topology between substrate, chip, and topside connection. We are using, as shown here, copper wire bonds. We can adjust the length of these copper wire bonds easily, and that helps us to adjust certain, I would say, certain spreadings you have on the chipsets, like various RDS zones or so. That helps us to compensate, and also some dynamic switching times where we can adjust then the aluminium wire bond on the chips. The connection to the outer world, the AC and DC connection, that's done with ultrasonic welding. Also there is no soldering in place, and the module itself has underneath, as I already summarized, a pin-fin structure. As that means you can use an open cooler. You can put the module directly there, and you can let the water flow through. Currently, there are extensive studies also running for closed coolers. Of course, then the power module itself has no pin-fin structure anymore. You would just have the DBC, and then you would either solder or sinter the module on a closed cooler. That's all possible. That's currently, we did in a lot of studies already some years ago, and we see now we have these both kind of requests, closed cooler, open cooler. We can support both with this module. Good. If we go then further to the applications, we have this wide range of applications. Of course, medium to high-end electric cars, very obvious. E-bus, e-trucks, what I mentioned. I think it's very important to keep in mind if you're talking about the medium to high-end electric car. A typical lifetime, required lifetime is 8 years, something like that, 8 to 15 years. If you think about an e-bus and e-truck, it might be massively longer, and especially in terms of kilometers. Medium to high-end car, maybe 400,000 kilometers, 500, something like that, as absolute 500,000 kilometers as absolute maximum. For an e-bus and e-truck, obviously, it is then over 1 million kilometers, as that means it's it's creating significantly higher requirements for the power cycling. It can be used in this e-bus with charging pantograph application. We call it TOSA. Used in heavy vehicles, railway, typically auxiliary converters, and marine shore to ship. And what is always fascinating to me as well, not listed here separately, but the power density of these road packs makes it also interesting for aviation application. So there are some of the road packs flying around in some of the e-aviation, of the electric aviation demonstrators. Good. As already shortly elaborated on, this module, even if it's pretty new, we started this 4 or 5 years ago, we have a lot extensive data in terms of lifetime power cycling, just to make sure that not only the medium to high-end electric car for 500,000 kilometers, but especially also the e-bus, e-truck, 1-2 million kilometers can be survived. And how this is typically done is that we start with the mission profiles. You see here 2 of these mission profiles, one German Autobahn highway, the other one speed race, where we see the current, the peak currents especially over time. With the thermal model and the thermal measurements, the thermal characterization we have done on the road pack, we can transform that to a temperature profile and have then, with this data, the chance with the lifetime models. And these lifetime models, they are done according to AQG 324, the well-known automotive standard for exactly such devices, where you really need to go for this PC min and PC sec, power cycling sec and power cycling min results. We do the power cycling min, we do 15 seconds on, 15 seconds off, and the PC sec, we are doing 5 seconds on, 5 seconds off. And as you might know, you have to repeat this test up to the failure of the devices, as you have to take a statistically significant amount. In our case, we took 6 devices, and we are running through these power cycles. With the 2 obtained operation points, it's then possible to create the lifetime models and to use that afterwards in the rainflow analysis based on the mission profiles provided to estimate the lifetime. And also, if you have a certain requirement, then to estimate how many % of the overall lifetime you are taking up with these requirements. Good. Then let's continue what is seen and what was detected as very important. Many of us, and also Hitachi Energy, we have a long experience with gel-filled modules for 20, 30, 40 years, using gel-filled modules, having a lot of experience of the behavior of the gel over time. But there is not so much experience with overmolded module, especially if you have overmolded module with quite a large surface, what is overmolded, also kind of the complete substrate with the chips and everything on it. And we invested significant amount of time for these button shear tests, also to do really the analysis and continue with this transfer molding analysis, just to make sure that there is a very clear and good contact between the epoxy mold compound and the module itself, also to make sure that there is no water, no humidity coming in. It's not hermetically sealed, and this is only valid, or is only available for bipolar devices, where you really have then the hockey puck, the ceramic housing. Also, it's not true that we could say it's kind of completely hermetic sealed. There is a certain edge exchange with the environment in terms of humidity, and this is important to be understood. Good. If we then continue to the road pack platform, and that's also something what is developing further and further. Obviously, it's not only the power semiconductor, the silicon carbide, or the silicon power semiconductor, the road pack itself, but it's also a lot about additional topics, additional devices you need around. One of them is obviously the gate unit. We decided not to develop our own gate unit, but we have been working together with 2 well-known gate unit manufacturers. One of them, Power Integrations, the other one, NXP. They have dedicated gate units that can be directly mounted on top of the road pack. They even fit in terms of size and the connection point, obviously. And therefore, it is very easy that you can use these devices, and you can build also up your desktop model, what you can use for first tests. In addition, what is in this platform is the Roadman cooler. I already mentioned there is a lot about cooling, especially open cooler. If you would like to get the best effect with this pin fin, you have to do quite some analysis on the flow, on the water flow or water glycol flow, and therefore we also provide proposals for coolers. Of course, they are also available as sample, especially for a desktop model or first design-ins. It could make sense to use this cooler. Later on, if it goes into a series design, usually the cooler needs to be adapted that it fits into the power inverter box. And therefore, we are supporting there with some guidelines, design guidelines, that all the lessons learned, all the design specifications we have in the cooler, that they are also later on available then on the power box. And then I will come to a little bit more details here also on the current measurement, especially for active short circuit. It is typically a requirement that you have also a very accurate current control and current measurement, therefore, directly related to it. And what we have is we added an add-on plug-in feature where you can have direct current measurement. And let's go in the next slide. Let's go a little bit more here in the details. That's how it looks like. Also, you can buy a standard road pack, and then you have this add-on. You see here even the clips, and you just clip it over the AC connection. You can even use the holes here that you can nail it down or fix it down with screws. So that means within the inverter box, the power inverter box, that you can connect it, that you can screw it on the cooler. And you see here, that's obviously the coil here. And here it is the prepared slot for the Hall sensor. And at the end, you can directly, you see here the cooler with the part of the pin fin structure, what is obviously from the road pack going into the open cooler. Then the connection of this current measurement bar, and on top you have the control PCBA, where you have the gate unit control, some maybe current regulation control, whatever you need, as well as the current measurement. And that's available with such an easy setup. That means you can also later on decide if it would make sense to add such a current measurement bar, or if you do it in another way. Obviously, this current measurement bar, you see it also, it is designed in a way that you can still do the welding and that you keep the inductances, especially the stray inductances, very low. Also, even using this current measurement bar, the current the stray inductance is on the connection itself is for sure lower than 1 nanohenry, and that helps to keep the overall stray inductance of the power inverter as low as possible. In terms of technical data, what is obviously very important here is that you have an excellent linear behavior, also that what you measure at the end after the sensor, that this is also representing the reality in current. It is quite a wide range of current you need to cover. You might remember the 2x10 chips road pack, the road pack L. It goes up to beyond 1000 amp, and therefore you really need to cover this complete area. And even short term, where you can go for double the current, that means 2000 amp, you need to be in a full linear area. Obviously, it needs to have a low error rate, especially also between different current bars, because you need 3 current bars if you have a 3-phase inverter, and therefore it needs to be reproducible directly already on the coil and the sensor itself. Of course, you can do some alignments and adjustments then in the software or in the amplifier circuit, but itself the device already should be within a very close tolerance. And last but not least, what is really important, that it is easy to integrate into existing gate units. So we are offering a sample where you have the current measurement bar plus the health sensor plus a small PCBA, where you just have everything what you need in terms of amplification and so on to read out this current measured value. But you can that's for kind of design in early stages where you would like to try out. But later on, it doesn't make sense that you have such a small PCBA, but that you can directly integrate this functionality into the gate unit, into the PCBA you anyway have there. Therefore, it's not only having or offering the sensor, the current measurement bar, and the PCBA, but also the design that you can take it over into your own gate unit or control PCBA. Good. Last but not least, obviously, if you think about charging and you remember the currents up to 1000 amps, that's a lot for charging, megawatt charging beyond. Obviously, that's typically too much, especially for some of the 50 kilowatt or maybe 100, 150 kilowatt chargers. And what we added to our portfolio as well is the so-called FlexiPack. The FlexiPack, as we call it, because it is, you can easily adjust it. You can also have different topologies. Some other call it EasyPack. We have two variants. We have FlexiPack 100 amp half bridge, and we have the FlexiPack 200 amp half bridge. We are only providing them with silicon carbide. We believe that this package is really good for silicon carbide. You can really reduce the strain inductance, do it to short bond wires and very close connections with the pins. You can make it very, very compact and very simple. It has no base plate. It has therefore also the possibility that you directly attach the DVC you have on the FlexiPack to the cooler. That either you screw it down and use thermal interface material, TIM, or that you solder it, or that you sinter it at the end. And that is what it is used for. You see here also the target data sheet. These devices, they are available. Feel free to reach out to GVA here. I think it's a very interesting package, and as the name implies, also it is very flexible. It's very variable. You can use it for various applications. You see here typically charging AC level 1, 2. That's the area where it goes to, but it can also be used in different other applications such as industrial, used in UPS, and so on and so forth. So there are various alternatives. Good. That's the overview from my side. Thanks a lot for your attention. It's great that you're part of this presentation. Please let me know if you have any questions, and I wonder how we can support you. Thanks a lot.
Thank you very much, Tobias, for this interesting presentation. This brings us now to the question and answer session. You now have the opportunity to formulate your open questions in the chat. Please make active use of it. And in the meantime, Tobias, maybe we can talk about the questions that came to my mind during your presentation. 1 year ago, it was a challenging situation regarding the SiC chip availability. Has the situation changed? Respectively, what has Hitachi Energy done to improve the situation?
Yeah, that's very good, Eric. You're absolutely right. You remember that was, I think it was not only affecting us, but many others as well. It was not so easy to get the silicon carbide chips in that volume what was requested for, and also in the quality. That was exactly one of the reasons why we said we are expanding now and supporting not only one chipset from one supplier, but many chipsets. And we have now also first customers. They started with a Wolfspeed Generation 3 as an example. And then they moved on to the next generation 3 Plus, as Wolfspeed calls it. And they are now preparing even for Generation 4. At the same time, they qualified ST Micro in parallel, just to be sure whatever happens on the Wolfspeed side, as one example, if there is no availability anymore, that they could change seamlessly to ST Micro. And with this setup, we have been able to kind of find a way and being able to deliver the volume what was requested over time, and therefore not to produce any line stops or something like that, just because there were no power semiconductors.
Okay, thank you. It was very interesting for me to see the FlexiPack. Is it planned also to add a silicon version of this package to your portfolio?
We have a lot of thoughts on that. We launched now the silicon carbide because we really see the advantage of the low strain inductance, as I said, and we also think it's an excellent package exactly for this purpose. It is possible, of course, to do it in silicon. There are also other manufacturers that are doing it, and I think there will be some news most probably later this year, early next year, where we also start to add then the silicon.
Mm-hmm. Okay. You mentioned the current measurement bar and the sensor integration and the possible design in. Is it possible to buy, for example, a demonstrator board for the customers for that design in?
Yep. Also that was always our target. We know that many of the first design-ins, they start really on a desktop next to the PC working space. And with the gate units, what you can directly mount on top of the road pack and connect it. Maybe with the cooler, just to have also a mechanical fixation kind of. The current measurement bar with this additional PCBA, what allows that you can directly connect and you can do the first measurements. You have a kind of full setup, what you can have then as a demonstrator set, or a design-in set, as we call it, on your desktop. And that's available, that's correct. Mm-hmm.
Okay. We have one question from our guest, Mario Berch. It's about batteries, the future developments in voltage and current density, and future challenges regarding road pack developments.
Yes. Okay. Thanks a lot for this question. It's a very good point. What we see, as I mentioned 4 or 5 years ago, it was typically 400 volt batteries. And that means the current was significantly higher because the voltage was limited to this 400. In the meantime, we see the step, of course, to 800 volt batteries. That means current goes down for the same power, obviously. And we see that there is even further optimization done with increasing the voltage once again. Also 950 volts, even close to 1000 volts. DC still to stay within the low voltage regulation. I think that's very important in a consumer vehicle like a medium high-end electric car. Where everybody is driving it. If you would have high voltage there, you would have to follow completely different regulations. But as long as you stay below this 1000, you can really optimize once again and reduce the current. Therefore, save a lot of copper, obviously, on the cables and so on, the motor as well. And we see a clear trend to go towards this 950 or even very close to 1000 volts. And the chipsets we are using, even they are called 1200. They have already a certain margin, especially for cosmic ray and low temperatures, that we can add this top on, that we are still safe with even higher voltages coming close from 950 to 1000 volts, something like that. Thank you for the question. Are there any further questions?
So there are no further questions in the chat. This brings us to the end of our webinar today. If you still have any questions, please do not hesitate to contact me or my colleagues from sales directly. You will receive an email with the contact details of our responsible employees afterwards. As experts in power electronics, we at GWA have, of course, even more to offer than semiconductors. In addition to the sale of a whole range of power electronic components, we develop and manufacture assemblies and systems entirely according to your specifications, usually in the range of a few kV up to the megawatt range. Feel free to visit our website for more information. The best way to follow us is on LinkedIn. This is the fastest way to find out more about GWA and its partners, as well as about our latest expert webinars. Tobias Keller and I thank you for your interest. I would be happy to welcome you back at one of our next webinars. Take care, goodbye, and hopefully see you soon.
Bye-bye.